All right, we're going to assume that we're recording here. All right, so we got a boat on the water, and we're going to talk about distance, position, and displacement. And I've been trying to talk about distance, position, and displacement sort of casually as we've been going along, but we're going to formalize it a little bit. First of all, when we're dealing with a situation like this, we want to deal with what we call a reference frame. And a reference frame, or a frame of reference, includes just defining what the directions are. So think of this like a side-scrolling video game, you know, like the old-time Mario Brothers type things. Sometimes that's like a mini game inside of the more modern games. We might have up, down, right, left as being some reasonable directions. And not only do we have to define our directions, but we have to define what directions are positive and negative. And it's almost like applying axes to the world. And recently I've been trying to drive home the fact that we're not totally married to the concept of X-Y axes. We want to have meaningful, situationally appropriate axes. Okay, so these reference frames, kind of like axes for the world, and meaningful and situationally appropriate. So up, down, left, right. Positive I'm going to make right. Up I'm going to make positive. That's fine. Now this boat's going to sail, and it's going to sail across the page towards this island. The fact that you're going towards the island doesn't mean that it can't be called the origin. The origin is really just a reference point. It's a point that we can make measurements with respect to. It doesn't mean where things came from. It just means that it's a point of reference that we can hold on to. A little bit of notation here. When I talk about position, I'm going to use the symbol D1 with an arrow over top of it, because position is a vector. It's got directionality associated with it. But when I talk about displacement, I'm going to use the symbol delta D with an arrow over top of it. Now delta is actually it's not this, no two alphabets are the same, but it's kind of like the equivalent of the letter D in the English alphabet. So we use the symbol delta in math class. We talk about y2 minus y1, x2 minus x1. Really, we're using the equivalent of a D from another alphabet to stand for difference. D is for difference, right? So the difference between two D values, the difference between two X values, the difference between two Y values. It's a difference statement, okay? So some people will say it's the change in. Well, change in and difference, synonymous things, right? So delta D means the change in position, how much the position has changed by. Fair enough, what's the difference in the positions? So I look at this and I say, okay, well, this boat, it's sailing along. And I say, well, at position 1, D with an arrow, 1, it's 15.0 meters to the left. So here I've got 15 meters, that's the magnitude in the units, and the left, the direction, to the left of the origin. And so always these measurements are made with respect to the origin. The origin is like our touchstone. Now, if I'm going to do math with this, I got to mathify this, because you can't subtract the word left. But that's why we put a positive-negative reference frame on things. So if we said to the left of the origin is negative, then we say, okay, well, left is code for negative 15.0 meters. So we're encoding those words as math. Okay? That's all. That's why we give a positive-negative to the reference frame. At some later point, I'll draw myself another sailboat here. I'll ask you to as well. At some later point, maybe we have a sailboat that's over here. And we can call this position 2 with an arrow over top of the D. And maybe it's at a position of 10.0 meters to the left of the origin. Somebody help me out. What should I write there? Negative 10.0, yeah. Because we gotta recode it as math. Only just so we can deal with it. Nobody can multiply the word up by the word sideways. That just doesn't make any sense. So we got to turn it into something that we can make sense of. All right, so then if I was going to deal with the displacement, I've acknowledged that displacement is a thing. What's the formula for displacement? Well, displacement, I was harping on this idea of it being the idea of a difference. It's D2 minus D1. And here I am, I'm defining displacement as a formula, But on the front cover of your booklet, there's a terms list. And so we're defining some things today. We're going to add some formulas to some things today. I'm going to suggest that this could be the beginnings of beefing up that terms list. Maybe you're going to add some things to the terms list. I've said before that the terms list was there initially to help people that were English language learners. But what I found is that people that aren't English language learners, English is your first language, really benefit from it as well because it's vocab, right? And it's hard to keep track of all these new words. A lot of them start with the same letter. And even the ones that don't start with the same letter have similar variables. And so like it's a tricky thing for everybody. So let's just make sure that we do have that. But that's going to be on you to maintain your own vocabulary list, but trust me, it'll be helpful to you. Anyway, when I sub in my values, I say, okay, well, D2, that was negative 10. I'm going to drop the 0.0 just because I'm going to run out of space. Negative 10 meters. And then minus, notice the minus is a part of the formula, just like it would be for y2 minus y1 in math class. So minus negative 15 meters. And negative 10 minus negative 15, what do you get? 5. Positive 5. Positive 5 meters. And of course, that's the math of it. But here we translated words to math. We should be able to translate math back to words. So if somebody said, well, what's your displacement? I'm obviously starting with a simple problem here. What's your displacement? 5 meters to the?
Right.
Yeah, to the right. Let's translate it back into words for humans. And we could even keep, it really is 10.0. Maybe I shouldn't have done that because we should be talking about how do we deal with our significant figures in our decimal places. Really that should be 5.0 because we're adding a single decimal place item to another single decimal place item. So 5.0 meters, right. Right, and that doesn't shock anybody. Like this is easy math, but I'm kind of going through the process so we can see how the mechanics of the communication work, right? All right, and then of course we'd say, therefore, the boat was displaced by 5.0 meters right. Nice. All right, more vocabulary. I've been talking casually about the idea of scalars and vectors, but I want to make sure there's no doubt about it. When we talk about scalars, we talk about something that has units, and we talk about something that has magnitude. Now, magnitude just means how big. So 10 has a bigger magnitude than 5. It's the numbers. An example could be 18 degrees Celsius. Could be 5 hours. Could be 17 kilograms. Notice all of those have magnitude, all of those have units, all scalars. When we talk about a vector, though, we say that it has units, it has magnitude, but it has this extra feature. What is it again? Direction, yeah. And so like what we just did, example would be 5.0 meters right. Another example could be like a velocity, v with an arrow over top of it, 80 kilometers per hour west. Yeah, you're right. Speed is a scalar because it doesn't have direction. So if we have a speed radar gun, some police officer says, oh, you were speeding. You were going at 90 kilometers per hour in a 40 zone. Oh my gosh, deadly stuff, right? They don't tell you that you were going east or west or whatever. They just tell you what your speed is. It's just a scalar. And so there is a scalar version, that's speed, and a vector version, that's velocity. And we'll unpack some of the subtle differences between the two. But yeah, definitely, one's scalar and one's vector. Keep in mind there's some slang. Like if I go to visit my mother-in-law and she lives in Toronto and I go over to her place, I could say, oh, she's 45 minutes east of here. What I mean to say is if I drive at the speed limit, it'll take me 45 minutes to get there and she lives to the east of me. But I say she's 45 minutes east of her. That's totally slang. I'm not saying that time, 45 minutes, has a direction. I'm implying a bunch of other stuff, right? So, you know, we gotta make sure that we understand the difference. And I think that most of us like implicitly do understand that, but like just to like put it all our cards on the table so we get that, you know, 45 minutes east of here is not a vector. It's like an implicit communication about how long it takes to get a certain place in a certain amount of time at a certain speed. All right, so
It's east in a different time zone.
oh, I guess, yeah. Yeah, there's lots of things that we can throw out there as examples where it's confusing. But anyway, let's just say that we have an old-timey sailor map. And somebody says, well, what's a reasonable reference frame for this? Well, oftentimes on these old-timey sailor maps, you'll have like a little cardinal direction thing like showing up on there. So I'm going to zoom in on it. And if I was going to zoom in on it, I might have north, south, east, and west. And for our purposes, it might make sense to have north be positive and south negative, east be positive, and west negative. That's not always the case. That's advantageous. I mean, if I was traveling towards Florida from here, I might make south be positive. You know, traveling down the east coast, that seems reasonable, right? If I was traveling from the mainland, let's just say at the position marked by the X, and I was trying to get over to an island, maybe there's treasure there, maybe my cottage is there, I don't know. For whatever reason, I need to get there by boat. I know that I could come up with a vector that would take me there. Now that vector, it actually might be the same situation as I have up above. Now this is a side view. This is perhaps the same boat, but an overhead view. And so we could say, oh, well, this island isn't very far away from the shore. Maybe it's a displacement of 15.0 meters. Same as the picture above, but viewed from overhead, I'm going to have to give us some more information. It could be that, you remember trigonometry from grade 10, it could be that I got to deal with, it's 40 degrees. Well, 40 degrees relative to what? The cardinal directions, of course, right? I mean, that's why we have a reference frame, so that we can have some sort of measurement of stuff like this. So, well, how would we communicate this? There's a method. So we say, okay, well, the displacement that this boat's going to experience from the shore all the way to the island is 15 meters. Okay, that's our magnitude and our units. I formatted this badly. I'm going to run out of space. So I'm going to write, it should go beside, but I'm going to write it below just because of my own formatting issues. The way I would write it is, open my square brackets, and it's almost instructional. Not almost, it's totally instructional. Look, if I was giving somebody directions, I'd say, okay, that 40 degrees. Point yourself east, and then rotate yourself 40 degrees towards which direction? North, right? So the way that I would write that instruction, east, 40.0 degrees north. And that's a little more complicated than just saying right or left, but it's really descriptive, and it's very intentional. And some people will say, well, wait a minute, what if you didn't measure it relative to the east? What if you measured it relative to the north? Anybody want to guess how many degrees away that vector is from the north?
50.
Yeah, 50. Now, I can't say east 50 degrees north. I can write the 50 in the middle. How should I write this? Yeah. Yeah, north 50 degrees east. Very instructional, right? It's just rotation instructions.
Go south 230 degrees west.
Nobody does south 230 degrees west. No, we always keep it acute. Right? always acute, always, between the two right angle reference frames. Anyway, that's situational. And this could be the same boat, but viewed from overhead, right? Like maybe it's a quadcopter, maybe it's GPS that we're thinking, or maybe it's an old-timey map. Here's a boat. This could be the same boat, but this time we're on the boat, right? So a different reference frame might be useful. So if we're on the boat,
Back left, right.
I hear the comment of front and back. So we can talk about forward, back. Maybe you're giving instructions to people that are your crew. We could talk about the right and to the left. Is there anybody who, I mean, I did kind of a scouts thing when I was a kid. Did anybody do cadets or anything like that? What are the terms that the nautical types would use for these things? Does anybody in the room know? One of them would be the bow. Stern, I hear it. Anybody know what are the sides? Yeah. Yeah, port. Now, you may have a hard time remembering this stuff. How do you know it? How do you... Oh, you're doing the sailing test. Or you're doing the boating test. Oh, okay, yeah. Port and starboard. But you know, this is a specific reference frame that boaters would know. And if you don't know port and starboard, probably you've heard of bows and sterns. But, I mean, when I was a kid and in the sort of scouts group, there was a gym game that we used to play, and the teacher or the scout leader would call out bow, stern, port, starboard, and we had to remember which end was the front of the boat and the back of the boat, and the gym was the fictional boat, right? And this was like, for some reason, this was important. If you're going to be learn how to set fires, learn the parts of a boat. This was going to be important for life, right? But really, what I take away from it now is that it's a reference frame. It's a situationally important reference frame because the boat can turn around in all different directions, and we need to know what the reference frame is in that situation. So there's all these situational reference frames, and you got to know what's appropriate. And so as we go along, we'll encounter different situations, and we'll have to decide what's the right reference frame. But in all these situations, I didn't do this, and we're not going to mathify this at all, but maybe we want to attach a positive and negative to each of these guys. Now maybe I'd want to make the port be positive, because I assume that's the side that you get off the boat on, being that it's called the port, but I don't know. All right, so when performing analysis and calculations, it's often useful to use signs, we talked about that, rather than words to indicate directions. So, for velocity, just in case we didn't catch it, we might have a velocity of 10.0 meters per second west. Now, sometimes people use just capital W. That might be okay or sufficient, depending on the situation that we have. And we might turn that, if we make east be positive and west be negative, we might rewrite that as negative 10 meters per second. That's cool. Displacement, delta D equals 5.00 meters right. We saw that up earlier on the page. And we could turn that into positive 5.00 meters. Now the dilemma gets into this two-dimensional stuff. You know, we saw this with the map for the first time, but it could be that you're traveling through a neighborhood. And if you're traveling through a neighborhood, it might make sense, north, south, east, west, to define your reference frame. Well, it always makes sense to define your reference frame. But let's just say you're walking through a city neighborhood or a suburban neighborhood. And as you do, you can't cut through people's backyards. At least you shouldn't. So we're sticking to the streets. And we might find ourselves in a situation where we get a displacement, call it delta D1. Then we get another displacement, maybe we call it delta D2. Then we get another displacement, delta D3. Because we're just, taking turns, working our way through the neighborhood. Now we all know, you remember in grade 9 or 10 you had to figure out how much baseboard you needed to use to finish off a room or something like that. There's these composite shape problems or something like that, geometry problems. We all know that we could take this delta D1 and this delta D3 and say, yeah, you know what? The amount that we traveled north is that amount. You see what I mean? Adding D1 and D3 together, yeah? We say, well, the only amount we traveled east was that amount, the equivalent of D2. And so we could say, well, really what we have here, I could put little arrows on here, really what we have here is delta D total in the x direction and delta D total, T for total, in the y direction. Cool? And if somebody came along and said, oh, you know what? This first one was 10 meters. The second one was 80 meters. This last one here, we went up by 30 meters. Then if I was going to take this diagram, which really is like a map of me walking the neighborhood, and I wanted to know my displacement, let's just agree that I could take this picture and simplify it. I could say, hey, I've got a delta D total in the x direction equals 80 meters. Then I would take my delta D total in the y direction. In this case, I'm not going to write a lot of math. Can we just like accept that 10 plus 30 is 40? Yeah? 40 meters. And I say, okay, well, from the beginning of the first one to the end of the last one, what I really did, you know, a bird could do this, but I can't. I went from this spot to this spot. And so my total displacement is the sum of all that stuff, right? That really is my displacement from where I started. That's how much I've been displaced. That's the change in my position. I just said the same thing a bunch of different ways, right? And I look at this and I say, well, this is just Pythagorean theorem, isn't it? Because by definition, north and east are perpendicular to each other. That's like a definition of the reference frames. So I'm right back to grade 9, grade 10 math. I can say, Pythagorean theorem is going to get me the length, the magnitude of that displacement. And SOHCAHTOA is going to get me the theta for that displacement. And we feel like we're in grade 10 zone already. How many people put their hands up and say, that makes sense to me? Right. Everybody. We've seen this before. Okay, so this is not new stuff. And we get ourselves a delta D total. Now, I'm not going to go through the math to do this right now. I just want to lay it out there to say, hey, look, we could make this ziggity-zag path into a simple triangle. And we're going to do a lot of turning zigzags and complicated, vector situations into something easier. Because it's all about making it easier for us, right? Another thing people talk about when they talk about this kind of motion is acceleration. And I haven't really talked about acceleration. But the symbol we use is lowercase a with an arrow over top. And actually, maybe I should draw attention to that. All the time here, I'm being really specific about whether I'm using lowercases or uppercases for things. And there are some people that are hard to convince, and other people take like half a semester to really like buy into it. If I use a lowercase, you use a lowercase. If I use an uppercase for variables, you use an uppercase. I mean, a simple reason for that would be like delta t, I use lowercase t. That's the change in how much time has gone by. If I use capital T could mean temperature. Capital T could mean the period it takes for a complete cycle to happen for a wave or orbital motion. Capital T means its own thing, okay? We got to make sure that we're situationally appropriate for our cases for our letters. And I know that seems like just an extra thing to keep track of, but case sensitivity for variables is a thing, okay? So if you're somebody who didn't realize that, you got to sort of realize that now, okay? Now, something that we did talk about was graphs. And so when I think about a graph for velocity and time, we might have like a velocity in meters per second. And this isn't a formal graph. This is just me hashing out a graph just to talk it out. I might have axes that look like this. 1, 2, 3, 4, 5. And I might have a time axis, 1, 2, 3, 4, 1, 2, 3, 4, time in seconds. And I'm not doing anything radical here. I just want to say that I could have a graph that by the 4-second mark, I speed up until by the 4-second mark, I'm going at 5 meters per second. Okay? Now, if I continuously speed up as time goes by, that's called acceleration. But then at the same time, we need to be able to mathify this, right? It's not just to be able to understand that speeding up is accelerating. I mean, by the way, slowing down is accelerating too, but sometimes we think of slowing down as being negative acceleration. But, again, I'm getting ahead of myself. Let's take a look at this graph. One thing that we know with analyzing position time graphs is that the slope has a meaning. And it turns out the slope for this has a meaning. If I look at the units, we know that the units for the rise will be in meters per second. And we know that the units for the run will be in seconds. And so if I think about this, the rise over run will be units of meters per second. And if I say, I'm accelerating at 5 meters per second, that means that for every second that goes by, I get 5 meters per second faster. So at 1 second, I'd be going at 5 meters per second. At 2 seconds, I'd be going at 10 meters per second. You see how that goes, right? That's accelerating. Now this one here, if I wanted to calculate the acceleration of this one, I could therefore look at the slope, and I could say, hey, let's calculate the slope. The acceleration is going to be the slope of a velocity time graph, where, remember, we don't use delta y over delta x. We're situationally appropriate with our variables, so it's delta v over delta t. And in this case, delta v expands out to being v2 minus v1. I'll putting arrows over top of my vectors, divided by t2 minus t1. And if I sub in my values, my v2, it looks like, was 5 meters per second. My t1, it happened to go through the origin, 0 meters per second. My t2 was 4 seconds, and my t1 was 0 seconds. And I've run out of space here, so forgive me, I'm going to pop up to the top. 5 divided by 4 is 1.25. Yeah, 1.25. And I could say, as I said before, meters per second. But then I got a person in the front row here that's just dying to say what the units are. What are the units actually?
Meters per second squared.
Yeah, meters per second squared. That's the units for acceleration, but I gotta talk about how we get to that, okay? They really are meters per second squared. And everybody writes it as meters per second squared, but meters per second divided by seconds ends up being meters per second, because really, dividing by seconds, we're dividing by seconds over 1. So meters per second times 1 over seconds simplifies to meters per second squared. So conceptually, I think it actually makes sense to think about it conceptually as acceleration being meters per second, your speed changes per second. That's what acceleration is conceptually. But the way everybody writes it is meters per second squared. Meters per second squared doesn't really deliver on the concept, But if I say my acceleration is 17 meters per second for every second that goes by, 17 meters per second, I think that explains it better, but nobody writes it that way. They always write it as meters per second squared. Decent sales pitch? That's all, okay? So we're just simplifying those units out. Let's take a look at the next page here. All right. So other things we got to think about. I know I'm unpacking a lot of things kind of all at once here. Other things we got to think about is that sometimes, let's say for example, we have somebody sitting on a cliff, and it's kind of fun sometimes to throw a rock off of a cliff, just to watch it fall. And as I do this, people remember, what's the name of that shape? Parabola. Yeah, parabolic motion. We do that with projectiles. We'll talk more about that later. But for reference frame, a reasonable reference frame might be up, and here I am. I'm putting my directions in square brackets, so when in doubt, you definitely can do this. Down. I'm not going to demand that they go in square brackets. Could be to the right, could be to the left, and so short forming right and left as R and L is reasonable. And it might make a lot of sense to make up be positive, to the right positive, down negative, and left negative. But then there's other situations, like for example, and I bet most people have found themselves in this situation, where you've got a spear in your hand, and a giant sea monster is trying to reach up and kill you. It's very common, right? And so your whole thing is oh my gosh, there's a sea monster, it's trying to kill me, Cthulhu is coming. Anyway, what you're not going to do is lob the spear, because sea monster is going to see it coming then. You're going to fire that sucker straight down, right into the heart of the beast, And in that situation, at no point does the spear go up. At every point, isn't it going down? And so, even though this is the same cliff, we're going to call down positive.